So we'll begin looking at the electrochemistry tutorial sheet. We have up to about 10 questions that we need to actually have a look at. So at the end of this video, you should be able to answer all these questions without any challenges. Okay, so the students that are registered, you already have learned the entire topic, all the basic concepts about electrochemistry. So these are just like extra questions to review if you've understood the entire topic. So question 1 says, in a galvanic cell, do electrons travel from the anode to the cathode or cathode to the anode? And we need to explain that. So electrons in a galvanic cell travel from the anode to the cathode. So on the anode, that's where oxidation occurs. And then at the cathode, that's where reduction occurs. So one way of easily remembering this is oxidation is loss of electrons, reduction is gain of electrons. So oxidation will occur at the anode, where electrons will be lost, and then they'll move using a wire to the other side where they'll be gained to cause reduction. So I believe we've answered that question. So why is it so? So one way you can think about it is because oxidation occurs at the anode, and then at the cathode, that's where reduction occurs. Question 2 says, how are standard reduction potentials combined to give the standard cell potential for a spontaneous reaction? So in a galvanic cell, you have two half cells, okay? One is oxidation, the other one is reduction. Now, they are all originally written in form of reduction potentials. So I actually have a list of them. So if you look at these, you can see that electrons are appearing on the reactant side in all these equations, which indicate all these are reduction half reactions. Okay? So in a galvanic cell, you are supposed to have two equations. So if you have two equations, a galvanic cell, one thing that we know is the reaction is supposed to be spontaneous, meaning that the cell potential is supposed to be positive. Okay? So let's take two examples here. If let's say you had the copper with 0.34 volts, and then you also had zinc with negative 0.76, how is that going to be? Which one is going to be the anode, which one is going to be the cathode? So if you reverse one, the sign of the reduction potential changes. Okay, so which one should we reverse between the copper and the zinc, so that after adding them we should still get a positive answer? So if we reverse the copper, both are going to be negative, so it just give us a negative answer. Now if you reverse the zinc, it will become positive 0.76, and then if you add it with a 0.34, it will give us a positive result. So in this case, that tells us if we reverse zinc, zinc will now appear as an oxidation reaction, because we would have to start with the solid giving us zinc ion plus 2 electrons emitted, which is an oxidation reaction, and it will have a positive reduction potential, which is now of course the oxidation potential, if that does exist. Okay, so now in other terms, to answer the question that we have at hand, instead of reversing this, you can think about it as so you expect zinc to be on the anode because it is undergoing oxidation, and then copper to be on the cathode, to be at the cathode. Okay, so if we are to determine the E cell potential, instead of looking at it as addition, the other way you can reverse is by adding a negative on the part we have reversed. So where have we reversed? We reversed on the anode. So in other terms, it's cathode minus the anode. So the negative changes the sign of the value of the reduction potential at the anode, because it's supposed to be reversed in other terms. So how are standard reduction potentials combined to give? So it is what is at the cathode where reduction occurs, the equation that remains as it is, you change the sign of the anode. So that's how you get the standard cell potential after combining the reduction potentials of the half cells. Oh, we're supposed to actually scroll down. So we can go to question 3 just before we go to 4. Well, the third question says if the E cell of copper had been chosen as a standard reference electrode and had been assigned a potential of 0.0 volts, what would the reduction potential of the hydrogen electrode be relative to it? So what would be the reduction potential of the hydrogen relative to the standard reference electrode, arbitrarily the copper 2 plus? So if we go to the reduction potentials, we can actually see that hydrogen is actually the actual standard reference, and it being a 0, we have copper being somewhere above 0.34. So we can actually see that the difference we have is 0.34. Now if we take the 0 to the part where we have copper, if that becomes 0, then we expect that going down we have negative, so we expect this one to be negative 0.34. okay, because basically that is a difference that is there between copper and hydrogen. Okay, so equally, if we chose, let's say, any value on top, let's say if we chose if we chose iron there, the same would be true. If that becomes 0, then going to hydrogen, the difference would be negative 0.77. So therefore the answer is this negative 0.2. So one thing that you know is when they give you such a question in your exam, they'll just give you this equation for copper, the half cell. So they'll put 0.34 volts. So you know that originally hydrogen is actually the standard, right? So you understand that hydrogen is just 0 volts. So if that is the case, if now copper becomes like 0, and since you know that copper was actually 0.34 higher than hydrogen, so if copper becomes 0, then hydrogen is supposed to be less by 0.34, which makes it to be negative 0.34 volts relative to a copper of 0 volts. So that's the answer. Now if we look at question 4, we need to make a sketch of a galvanic cell. Okay, so we've been given the shorthand of a cell notation. So how do you convert that? So usually the left is usually the anode, that is the cathode. We can actually make a confirmation by looking at the potentials that we have. Let's compare iron and is it silver. So if we check where iron is, that's where we have. Then Ag, which I believe should be gold, is 0.8. So which one should we reverse if we are to maintain a positive answer? Remember, this, since these are both positives, if you reverse it, it's supposed to become a negative. So we should reverse one that is less, so that we still remain with a positive answer. So the ion will be reversed, making it the anode, right? So that's confirmed. So this remains the anode because it's supposed to be reversed. That is the cathode. So make a sketch of a galvanic cell. So something like this. Two different solutions. We can make sketch of the electrodes on both sides. We can have a wire joining them. Okay. So electrons flow from the anode to the cathode. So this is the anode, that is the cathode. So on the anode, we've said that's where we have silver, that's where we have iron. Sorry. Okay. And then the other side will have the solid as well. Then in the solution, here we have the ions equally on the other side as well. Then what is missing? We need to put a salt bridge. Let me use Okay, so a salt bridge that was used, it was not specified, so you can just label it to be a salt bridge. So that alloy is indicating the flow of electrons. Okay, so indicate the charge on each electrode. So which one is expected to be the positive, which one is expected to be the negative? So the anode is actually negative because this is where oxidation occurs, and so electrons will build up. Then the other side, it is actually a positive, which will now attract the electrons from the other side. Okay, so we've indicated the charge, indicate the direction. Okay, we have indicated direction. Write the balance equation. So a balance equation now. Okay, so I can erase the galvanic cell. So the half cell for the first part on the anode is oxidation. Oxidation is loss of electrons. So we have from the solid giving us production of the ion 3 ions plus emission of 3 electrons. And then for the other one is reduction, so gain of an electron to give us a solid at the cathode. So we need to balance the number of electrons, so multiply by 3 and by 3. So if we get to add these, we are going to have ion solid plus that equal to. So I'm adding the reactants and the products. Okay. So the number of electrons being lost and gained are supposed to be the same. So if combine this with this to give us the products, that and this to give us the reactants, and that is the balanced equation. Question 5 on the other hand is also asking us, so you are supposed to write the half reactions and also the balanced cell reaction for the following galvanic cells. So whenever you see platinum, in most of the cases, it's because the actual half cells or half reactions don't have the solids that may represent them. Okay, I don't know if that makes sense. So it's like you only have aqueous, so you can't have an electrode being in aqueous state. An electrode is supposed to be in solid form. So if you don't have it, what basically happens is you use a non-reactive metal like platinum to represent the electrodes. So on both sides, I believe we didn't have solids in the half cells. Okay, so we need to write the half cells. So if you look at the first one, what is half cell? So we have that and that. So usually on the left we present the anode. So we have ion 2 plus, okay, giving us ion 3 plus. So taking the left to be the anode, we expect that there will be an increase in the charge because that's where oxidation occurs. Oxidation occurs at the anode. So oxidation means loss of an electron. Loss of electron. So why have I put a single electron? Because we are moving from a 2 to 3, which means a single electron was lost. What else is remaining? For the other side, NO3 giving us what? Plus the hydrogen that is there, which is a reduction in itself, giving us NO in gaseous state. So I believe this is aqueous. So is that balanced? We can clearly see it is not balanced. How do we balance it? So if we check, here you've got 3 oxygen atoms. There you've got a single oxygen atom. So we balance oxygen by adding water. So we're going to add 2 more water molecules on the right to ensure that we have an equal number of oxygen atoms. And then we can also add, since we've introduced hydrogens there by introducing water, so we have 4 of them on the right. Here you've got just a single, so you can put a 4 to the hydrogen, which I believe now gives us the balanced half cell reaction there. anything missing. So at this point we need to observe a number of electrons. We need to balance the number of electrons in both equations. So in the second half cell we've not shown the number of electrons. Let me just clearly put that. So I've got 4 hydrogen ions there. So here we've got a negative there, we've got 4 positives. The overall charge becomes positive 3. Then the other side there's nothing. So we are moving from 3 going to a 0. That is clearly reduction, meaning that 3 electrons were actually gained. So equally we would have to multiply the other part by 3 as well to balance the number of electrons that were being emitted. Okay, so electrons can cancel out, and then we can equally do the same, combine the reactants together. Okay, so even without wasting much of your time, I can just, so the balanced equation is just going to be 3Fe2 plus, and then on the other side I can just add the other one from the other reaction, ion as well. So what is the balanced equation? Don't forget to indicate the states: aqueous, aqueous, aqueous. And then we need to look at the other part. So you can actually, in most of the cases, they may actually give you the half cells, okay? But in this case where we've asked, it may be very difficult for them to give you. But since for practice you can actually confirm with the table, you look at the values that are there to see if you were right in terms of your calculations. Okay, and you can try to look the half cells we had actually indicated there. Try to look them up somewhere. Okay, so the other one, feel free to try it out. Try to indicate the half cells that are there. So we expect this again on the left. Of course, this is like a short bridge. So this is the anode, the other side is expected the cathode. So anode, oxidation occurs. So the solid is supposed to lose an electron to give us an ion. I'm looking at the positive and the 0. So that is like loss of a single electron. On the other side, reduction. So nickel 2 plus gains a hydrogen, that is reduction in itself, giving us NO2. Is it balanced? Not at all. We need to balance by adding something. So we need to add 2 water molecules to balance the oxygens. So 2 water molecules. What else? We've introduced the hydrogens, so we need to add 4 of them. What else? So the moment we do that, here we've got 1, there we've got 4. So we'll actually get to cancel. And then our men are going to remain. Are they going to cancel? Let's wait. So you've got like 4. So plus that one makes it 5. So I'm actually supposed to put 5 there. But because of this one, which is going to cancel with one of them, it will still reduce to 4. So this will just say, we can just cancel that out. So that you remain with 4 and 4. Okay, what else? Are we balanced? Okay, so we've seen one is reduction, the other one is oxidation. So let's try to see how many positives we have here. You've got 2 positives. Then on the other side you've got 4 positives. So this is now again where the issue comes. Let's try to see. Nickel has got 2 plus. The NiO2 is there any charge there? Okay, so there's no charge. So if we expect this one to be reduction, we're not supposed to actually reverse it, unlike the way we've put it. So we have NiO2 appearing on the left, plus the 4 hydrogen ions, giving us 2 water molecules plus nickel 2 plus. So electrons will appear here now. 2 electrons were actually gained. So for us to balance the equation, we need to introduce the 2 on top there, so the electrons are actually balanced. And then the full reaction will now involve this one coming to be part of the reactants, that one coming to be part of the products. The electrons are supposed to be removed. So then you have your full balanced equation for question 5. Question 6. Aluminium would displace tin from solution according to the equation. What would be the individual half cell reactions if this were the cell reaction for a galvanic cell? Which metal would be the anode, which the cathode? Okay, what would be the individual half cell reactions? That's a very simple question to answer. Okay, so look at this one and that other one. So I've got 2 aluminium solid giving us aluminium 3 plus. So that is radio oxidation. How many electrons are these? So try to check. There I've got a 0. There I've got like a 3 plus times the 2, 6 plus. So 6 electrons were lost. Okay, so that is like, if you go back to the actual half cell without the balancing of electrons, it would be just aluminium solid with 3 electrons, but balancing the electrons, we have 6 electrons. And then the other cell for the tin, okay, so there we expect to have like 6 actually this is like reduction, so electrons were being gained, 6 electrons were being gained. Okay, that is the half cell. So these are the 2 half cells that were actually there in this reaction after the balancing of electrons. Which metal would be the anode, which the cathode? This is very simple for you to actually make an observation. So which one is oxidation? So oxidation is the first one. So aluminium is oxidation. So aluminium solid would be the anode. The cathode would be tin solid. Okay. Question 7. The cell reaction during the discharge of a lead storage battery is that the standard cell potential is that. What is the correct form of the Nernst equation for the reaction at 25 degrees Celsius? So the Nernst equation, I believe you know what it is. So it helps us to calculate the non-standard cell potential, okay, to be dependent on the standard cell potential minus RT over NF, number of electrons multiplied by Faraday's is constant, natural log of Q, where Q of course is like the quotient of the reaction. So this is going to be easy. So the standard cell potential has been given to be 2.05 minus RT. So the R there is already known to be 8.314. The temperature 25, you add the I'm not forgetting this. So anyway, 25 degrees is equal to 298 Kelvin. You add like you add a 275. So 298 kelvins. The number of electrons, if you check the number of electrons there, so if you know just the number of electrons that actually were being transferred from one half cell to the other are 2, and then the Faraday's constant is 96,485. So the other part will have natural log. So N determines the number of, looks at the number of electrons, F looks at the Faraday's constant, T is the temperature in Kelvin, R is a gas constant, and then natural log of Q. So Q looks at the aqueous and gaseous states. So water was actually in liquid. So the only substance that qualifies to be part of the quotient is only sulfuric acid. Now, what does that mean? So we know that it's actually products over reactants. So all the wait, am I actually right by saying that only the sulfuric acid is supposed to appear? I can see the hydrogen is also in aqueous state in this case. Okay, so what we might expect is the solids and the liquids, you take them as ones. Okay, so that's why we say, in other terms, we say only the aqueous states and the gaseous actually appear in the K or Q expression from the study of chemical equilibrium. So for the products, we don't have anything in gaseous or aqueous, so just put a 1. Of the reactants, we have hydrogen plus raised to the power 2, and then also sulfuric acid raised to the power 2. Remember we said the concentrations are supposed to be raised to their stoichiometric coefficients. So this is the expression of, so if we are given actually the concentrations of the hydrogen and the sulfuric acid, we are going to actually even get to perform the calculation and determine the non-standard cell potential of that battery. Okay, so we are on question 8. What are the anode, the cathode, and the net cell reactions that take place in a nickel metal hydride battery during discharge? And then what are the reactions when the battery is being charged? So during the discharge, some of these things there's nothing to explain. So actually, a nickel metal hydride, so the metal is not actually specified, but we'll take M to represent the metal. So during the discharge, the metal first reaction on the anode will be the metal reacting with hydroxide to get the metal hydroxide, and then an electron being okay. Question 9 now is a question we are looking at. How many hours would it take to produce 85 grams of metallic chromium by the electrolytic reduction of chromium 3 plus? How would we answer that question? I think this is electrolysis. I actually made a very long video about it, so it shouldn't be like a struggle for most of you to basically get to figure it out. I think what is also important here is to understand the equation. So we have metallic chromium by the electrolytic reduction of that. So I believe the equation is you begin with chromium 3 plus and then being reduced to chromium metal. So we can say chromium 3 plus gains 3 electrons obviously to give us chromium in its metallic form as a solid. Okay, so we can see we have got 3 electrons here. So we need to determine the hours. And then we have question 10. Question 10 says A large electrolysis cell that produces metallic aluminium from the aluminium ore by the Hall-Heroult process is capable of yielding even up to 409 kg of aluminium in 24 hours. So by the way, this same process, I don't even know how to pronounce it properly. This same process is the process by which metallic aluminium is produced commercially, okay, from the ore itself. So the actual equation is the aluminium ore. I don't know if this is used to be called bauxite, I've forgotten. It should be called bauxite, yeah. It's one of anyway, so the action with carbon gives us the metallic aluminium and carbon dioxide. So this is actually the equation. Okay, now one thing that is actually stands out for me is the fact that this is also electrolysis. So whatever we applied in question 9 can be applied to answering this question. So except here we're trying to determine what current is required. So let's look at the details that we've been given. So here we've been given the mass, you have got the hours. What else do we have? I think that's the only information we have, but I believe from the periodic table we should be able to get like the molar mass. From the equation we should be able to see the number of electrons that are being transferred. If you get any of the half reactions,